Hello! This week we're going to start taking a look at splines and how you as a coder can use them to enrich your applications and games. In short, splines are a way of algorithmically representing a curve. And even though you might not think you need curves in your application, you'll be surprised just how useful they can be. For example, if you're making a game, why do your game objects need to move in straight lines? They can look a lot more fluid and natural if they follow a curvature. What if you're interpolating between 2 points? Again, don't use a straight line, use a spline. You've probably already encountered splines and don't really realise it, so here in Humble Paint this is a spline and we can position the curvature. And you've probably experienced the frustration of trying to curve it just how you want it. It always seems to have a mind of its own. We see from the paint example that we'll have 2 control points and a third one, which is used as an indication of where the curvature should tend towards. And if we were trying to represent a longer path using more points in this fashion, we have to pretty much guess where those control points need to be. We'll also face issues about what happens when you try to join 2 splines. If we have a look at the Wikipedia article for splines, we'll see that it's actually quite mathematical. And this can make it inaccessible for the one-lone coders out there, who just want to get some curvature into their application. That said, the maths behind these things is quite fantastic, and we'll be looking at some of it. But when it comes to programming, we rarely like guesswork. So deciding where to put these control points is not ideal. So we'll not use that type of spline. Instead, the type of spline I'm going to be explaining in this video can use multiple control points, and the path is guaranteed to go through all of them. And to use this, I'm going to use a type of spline called a Catmull-Rom spline. And an interesting fact here is the Mr. Catmull in the Catmull-Rom here is one of the founders and current president of Pixar. So this guy knows his stuff when it comes to computer graphics. In its most basic form, a Catmull-Rom spline contains 4 points, which I've denoted here with the red, blue, orange and green dots. Just to get us going with some of the notation, we usually refer to it as P0, P1, P2 and P3. A Catmull-Rom spline will only generate a curve between P1 and P2, and it uses P0 and P3 as a guide to what angle the curve should be going through the points P1 and P2. To find a point along the spline, we usually use a value t, which begins at 0 for point 1 and ends at 1 for point 2. So we're accessing the curve segment in normalized space. And the nice thing about Catmull-Rom splines is the points can be multidimensional. So even though we traditionally would have x and y, we could have more dimensions afterwards. And the mathematics doesn't change, it just scales up. So I'm going to try and start explaining how a spline works without getting involved with the mathematics just yet. And I find it useful to think about the points as being the centre of influential circles that guide our point t. So simply put, as we approach P2, we're more influenced by P2. And we become less influenced by P1 because we're further away. So of course, if the point lies directly in the middle of P1 and P2, we're equally influenced by both the points. And if the point on the curve we're interested in happens to lie on one of our control points, we're 100% influenced by that control point and nothing comes from the other control point. So what are points P0 and P3 for then? Well, if we just had the points P1 and P2 influencing the curve, we would get a straight line, which, you don't need me to tell you, isn't a curve. So in a similar way to the circles of influence from P1 and P2, P0 and P3 also are influencing our point on the curve, but in a much more mild way. So whereas we saw P1 and P2 attract our target points, P0 and P3 repel the target point. And we can see in this example that the curve pushes upwards. Using the desmos.com graphing calculator, we can have a look at the maths behind the spline. Consider the x-axis along the bottom to represent our variable t in normalized space, so it goes from 0 to 1. And if we remember for our point that was blue, which is P1, we want to have a full influence when we're on the point, and we want to have no influence at all when we're on the other extreme of the curve, in this case P2. So in this way, consider the y-axis to be the amount of influence the point has on our point T going around the curve segment. Naturally then, it follows that our orange point, which was P2, has an opposite looking curve. So it is not influenced at all by P1, but as we increase our T point along the curve segment, it becomes fully influenced by the time it gets to point 2. Let's consider P0 now. This one looks a little strange. Positive influence in the y direction is attraction, i.e. we bend the curve towards the point. So P0, the red point, here goes negative, which pushes the point away, as I showed with the arrows before. And likewise, we have a mirror image curve for P3, the final point. All of these functions are cubics, so this is a cubic spline. If you've ever tried to use the pen tool in Photoshop, you'll know why this is important. At each spline control point, we can specify a gradient, but the curve doesn't necessarily go through the points. This makes this tool incredibly frustrating to use. But it does highlight one of the limitations of the Catmull-Rom spline, that we cannot specify the gradient through a point. The gradient is always calculated by the position of its neighbouring points. These equations are only valid for one component of our point vector, so in 2D space we'd have to calculate all of these for x and all of these for y, to give us the xy point on the curve segment. I think it's time to start putting these into practice, so I've created a new console project. And I'm going to use our old friend, the OLC console game engine, so we can visualize the splines. As most of my viewers will know by now, the OLC console game engine just simply wraps up the console in a way that it repeatedly displays information to the screen. And it also accepts some user input. And we need to override two functions in this class, the onUserCreate and onUserUpdate functions. I'm going to create a console application that's 160 characters wide by 80 characters high, and each character in the console is going to be 10 by 10 pixels. Let's start by creating a structure that represents a 2D point. So I'm just going to have an X and a Y coordinate. I'm going to create another structure now to represent the spline. And the spline is going to consist of a vector of points. Let's start by getting some of the visualization out of the way. In my game engine class, I'm going to need a spline object, which I'm going to call path. And in the onUserCreate function, I'm going to populate that path with points. So these are coordinates of console characters on the screen. And they represent the control points in the spline. There's only 4 of them. Now let's try to draw these to the screen. The first thing I'm going to do is clear the screen, which I'm doing by drawing a space to all characters. Then I want to iterate through all of the points and draw them. To do this, I'm going to use the fill function to draw 1 pixel either side, or 1 character either side, of all of the control points. It's going to use the solid character and it's going to colour them red. This will give me a 3x3 block to represent a control point, and in the middle of that 3x3 block I'm going to draw the index of that control point so we can see which one's which. Let's take a look. Perfect. I want to move the control points around the screen, so I'm going to create a variable that represents a point that's selected for movement. We'll initialize it to 0. So let's handle a little bit of input from the user. If the user presses the X key, I want to increment my selected point variable, but I'm also going to make sure that it doesn't go out of bounds, so if it does, it rotates it back round to 0 again. I'm going to do the opposite with the Z key, which this time decrements the variable. Now I want to move the selected point around depending on the arrow keys. So I'm going to check if an arrow key is held down, in this case left, and if it is, I'm going to move the selected point's X position by some value. In this case, I'm picking 30 because it will be a fast movement, and if I modulate that with the elapsed time, it'll be smooth depending on the performance of the system. And likewise, I can do the same for the other arrow keys. I think it's important that we highlight the currently selected control point. So I'm going to use exactly the same code as I've done here, except instead of colouring it in red, I'm going to colour it in yellow. And obviously I'm going to use the selected point variable instead of the I in the loop. Let's take a look. So we can see the 0 control point is currently highlighted, and I can use the arrow keys to move it around. And if I use the Z and X keys, I can move any control point that I want. So how do we draw the curve? I'm going to create a function called getSplinePoint, which takes in a value t and returns an xy coordinate. For now, I'm just going to hard code that as 0, 0. Drawing the spline is a little tricky, and I want to make sure I'm drawing it behind the control points. Remember, we're using the curve to generate an xy position based on a normalized coordinate, so we're going to issue a 0 to a 1 and it will return an xy for that point on the curve. So let's create a little for loop which iterates from 0 to 1. And I'm going to nibble at it in very small steps. And we'll see that this is actually one of the downsides of using splines. For each value of t, I'm going to call our Spline Point function, which should return the xy coordinate, and I'm just going to draw a pixel at that xy coordinate. But of course at the moment, it'll only draw something at 0, 0, because we need to fill in our getSplinePoint function. We've only been given the value of t, so we need to create some indices based around that value t. We know, for example, if t was, say, 0.3, then p1 would be the floor of t, which in this case would be 0. From there, we know that p2 is p1 plus 1, we know that p3 is p1 plus 2, and we know that p0 is p1 take 1. So let's do exactly that. I'm just going to cast to an integer to do our floor equation. And of course, because I code these things live, I've immediately noticed a mistake. It's p0, 1, 2, 3. We can now start to implement our equations. So I know that I'm going to be using t squared and t cubed a lot, so I'm going to cache these. And I'm just going to take the equations exactly as I had them in the Desmos graphing calculator to give me 4 values which are our influential field values. To calculate the result, we do it one axis at a time. So I'm going to look at the x-axis first. We need to take the point that we're interested in, so in this case the first one is p0, and we're only looking at the x coordinates at the moment. And we'd multiply that by our first field of influence, which was the red line, the red point. And then take the next point along and use our second field of influence, and so on. So the 4 influential fields are multiplied by their respective point locations in the x-axis. I can cut and paste this to do the y-axis, and just change the x components to y components. And instead of returning 0, 0, we'll return tx, ty. There is one final thing to do. If we examine these equations, we see that the influence on the y-axis lies between 0 and 2. We want this to be between 0 and 1, so we will halve all of the values. Let's take a look. Well, there's certainly something on the screen. Let's see if it's behaving. So I'm going to move this control point down. We can see it does start to repel some of the curve. Let's move this control point over a little bit. There we go. And we'll bring this one round too. So we'll make it look like we had on the diagram before. However, for some reason it's a dashed line. Why is this? Well, that's because we nibble through the 0 to the 1 in a small increment, and if we're only incrementing in 0.05, that means really we can only have 20 pixels between the two control points, and if they're 40 pixels apart, we'll skip every other pixel. So we need to make this smaller. Let's have a look. That's better. That one curve segment on its own isn't very impressive, so let's add a lot more points. So here I've added a point every 10 pixels in a straight line. We've now got more than one curve segment, so we need to adjust our drawing routine accordingly. Now I take the number of points in our path and I'm going to use that to calculate my t. Note that I'm subtracting a value from them. I don't want to draw the two control points at the end of the spline. Let's take a look. Something doesn't look quite right here. Oh dear. Let's see why this might be. Well, our t is going to go above 1. So we need to modify our getSplinePoint function to accommodate this. And this is quite simple, because we've already got the floor of our t to give us our first control point. We just want what's left over. So our control points will represent 1, 2, 3 and 4, and any remainder that comes in is what we're going to use to index into the normalized point of the curve segment. This looks a little better. Let's move some points around. Very nice. And so you can see with more control points we can have quite elaborate curves. Let's just take a minute to look at an interesting property of this. Here I've laid out the points in what appears to be a loop. And in fact, if I take the two endpoints, which in this case will be 1 and 8, and overlap them, that would actually make a loop, but it's a loop with a bit of a kink in it around the point 8. But I can get rid of that by using the two original endpoints and overlapping those with the two neighbouring points, which gives us a nice perfectly curved loop. And so if we wanted our splines to be loops, we could just manipulate the indices when we're trying to calculate our spline point, and therefore we know that our loop goes through all the control points. If we want our spline to be looped, we have to treat it differently. So I'm going to modify our spline point function. If it's not looped, we just do what we did before, which will give us a curvy path, but the ends won't join. But if it is looped, we can take our t variable, calculate the indices in a similar way to before, but this time wrap the indices around all of the points in the vector. So let's say I'm approaching the point towards the end of the vector, I can use the modulus function to wrap it round to the start. And likewise, if I go below 0, I can't use the modulus function for that, but I can do a little trickery here to give me the point at the other side of the vector. We should also modify our drawing function now to go through all of the points, but we must tell our spline function that it is looped now. Let's take a look. Well, it looks like a straight line again, but as I start to move the points around, we can see they're certainly joined. Nice. Now we have a facility where we could control an AI character, let's say for example a spaceship, to follow a path around space. And it will look very natural, it won't have to move at right angles or turn at fixed intervals. And the path can be modified in real time. So with a simple bit of mathematics, we can generate a very natural looking behaviour. But what if we wanted our spaceship to follow the path precisely? For example, in this instance, our spaceship is only getting an x and y coordinate, will always point in the same direction, regardless of where it's up to on the path. Instead, what we would prefer is that the spaceship carry on pointing in the direction of the path, depending on where it is. And we can do this by extracting the gradient at any point. A crude way of getting the gradient at a point would be to take its two control points and create a straight line between them, and that would give us an approximate gradient, maybe. But a better way is to modify our spline equations to give us a precise gradient, in a similar way that we calculate the position. Unfortunately, this is very simple indeed. If you remember before, we were calculating our q values, which were the influential fields, so we have something like minus t cubed plus 2t squared, take 1. All we need to do is differentiate this equation, which becomes minus 3t squared plus 4t, take 1. And we can do that for all of our equations. So I'm going to take our entire point function here and duplicate it. I'm going to call this one get spline gradient. And everything else can remain the same, but I'm going to change these equations. So I'll just cut and paste the others in. There we go. So let's hack something in to demonstrate that we can extract the gradient. The agent's location is going to be represented by a variable called fMarker. So we need to add some keys so we can increment and decrement this variable. I'm going to use the A and S keys to change it. But I want to make sure that I keep control of this variable, so I'm also going to put some boundary checks in. So if the marker value goes larger than the number of points in the path, then it wraps round, like we did before with the Z and X keys. I'm going to draw on our path where the agent currently stands. So to do that, I'm going to get the point on the path. This assumes we're looping at the moment. I'm going to get the point on the path where the marker location is, and I'm also going to call our getGradient function for the same point. To draw the agent, I'm going to draw a line which I'm hoping is going to be orthogonal to the path at all points. So let's have a look at this. The first thing I do is calculate the angle of the gradient returned by the getSplineGradient function. So this will return an xy vector, but I'm going to convert it to radians. And I'm going to use the drawLine function, which is provided by the game engine, to calculate 2 points that are rotated around P1, which is where our agent is on the path, by the angle represented by the gradient. I'm going to offset these by 5 pixels. So I'm going from one point here, which you can see is +5, to a -5. And this will hopefully give me 2 points either side of the path. I'm going to draw this blue. Let's not also forget that we're working in looped mode here. So let's take a look. Well, I can see the agent is definitely orthogonal to the path. So let's make our path a little bit more interesting. It's always very satisfying watching the curves sort of unfold themselves. And we can see the agent starting to rotate, depending on the orientation of the path. So if I use the A and S keys, we can see the agent follows the path now, because I'm incrementing its position along the curve. And it wraps round. Very nice. So this video has shown you how to create a path and spline between all the control points. And I think it's quite useful for things like non-player character AI or animations. But there is still a few things to work out. So as I move my agent around, we can see his speed varies. And this is because it assumes that the distance between all of the points is the same, 0 to 1. We'll come up with a solution for this in part 2 of the Splines video. All of the code for this video is available on GitHub. If you've enjoyed it, please give me a big thumbs up, have a think about subscribing, and I'll definitely see you next time, and I'll definitely see you for part 2 of this video. So take care.